Okay, so we're looking for a way to achieve this simultaneous transfer, continuous time, continuous space within our system. Here's what we've been working with so far. Picture a single dimension, we'll call it x. And arbitrarily, let's say x goes from 0 to 40. We're going to picture a series of tubes, glass tubes if you like, sitting along this spatial dimension. And I'm not going to draw all 41 of them, but I'll draw a few. And we can give each of these tubes an address based on where it is along the x-axis. So this will be tube 0, 1, 2, 3, 4. This might be 12, 13, 14. This is 39. This is 40. And these are playing the role of our memory locations in our traditional memory. Now we have a pair of fictitious chemicals. One is called S, or source, and we draw that in red. The other is called destination, DST, or D, and we draw that in blue. And the setup is each of these tubes contains some amount of S and some amount of D. So for example, tube 4 might contain this much S, and it might contain this much D. And these chemicals don't seem to mix, so the S is always on bottom, the D is always on top. That's just a convenience so that we can easily look at it and see how much of each chemical we have. It's totally a fictitious setup. So each tube has its own mix of S and D. So this has a lot less of each. This has very little S, but has a lot of D. And so on and so forth, or maybe these other tubes are empty. Now we can interpret the contents of each tube as an instruction. For example, this tube right here might have chemicals in the following concentration. Tube 2 might have source equals 1 and destination equals 12. And this tube here might have source equals 3 and destination equals 2. And this tube over here might have source equals 12 and destination equals 14. So this is a static snapshot of the system. And suppose that these are the only tubes with chemicals in them, all the other tubes are empty. What is this system about to do? Well, each of these tubes of chemicals corresponds to an instruction. It's a transfer instruction. With source 1, destination 12, this says transfer some chemicals from tube 1 to tube 12. Tube 3 says S equals 3, D equals 2. That says transfer some chemicals from tube 3 to tube 2. And tube 4 says transfer some chemicals from tube 12 to tube 14. Okay, let me throw some chemicals into tube 1. Let's say tube 1 just contains some destination. So tube 1, source equals 0, destination equals, let's say, 2. So tube 1 is saying transfer from tube 0 to tube 2. Okay, what happens if we let this system advance forward in time? Well, we're going to transfer chemicals from tube 0 to 2. Tube 2 is empty. That's a no-op. So tube 1 does nothing. All of these other tubes that are empty, source equals 0, destination equals 0, it's saying transfer chemicals from tube 0 to tube 0. That's a no-op. But tube 2 says transfer from tube 1 to 12. So we're going to take some of this blue chemical in tube 1 and move it over to tube 12. And tube 12 is going to begin to fill with destination, and tube 1 is going to begin to empty. At the same time, we're going to take some chemicals from tube 3 and transfer them to tube 2. So some chemicals will come out of here and go into this tube, and at the same time, we're going to take some chemicals from 12 and copy them to 14. Now right now 12 is empty, so copying from 12 to 14 is a no-op. But as we begin to copy from 1 to 12, we're going to see some source pop up in here, and this tube's going to say take that source and start transferring it to tube 14. And the idea is all of this happens simultaneously. So we've got the simultaneity of execution. And we do this over an infinitesimal time period. So we imagine advancing this simulation just a little bit in time so that we just get a little bit of chemical transfer. That's the discretization in time and the simultaneity. What about the discretization in space? Well, we'd set up these tubes to have a diameter of 1 and to have integer addresses. But what if we made these tubes have a diameter of 0.5 and gave them addresses of 0.5, 1, 1.5, 2, 2.5, and so on? Since the amount of chemical in here is a real number, we could have a chemical in here with a source of 2.5 and a destination of 1.7. And we can round these off and say, okay, 2.5, that's tube 3, and 1.7, that's tube 2, and we could transfer according to that. But again, shrink dx, shrink delta x down to a limit where it's actually dx, where we have tubes that are infinitesimally thick. And what's going to happen is we have a very thin tube here. And even though the amount of fluid in there is tending towards 0, there's still, relative to the diameter of this tube, we can assess how much source and destination we have inside here. So we might have source going up to here and destination going up to here. And it's that amount relative to the thickness of the tube, or if you like, the height of those chemicals in this tube, that we can attach meaning to. And no matter how thin this tube gets, we can still assign meaning to those quantities. So each tube contains a real number amount of S and D, and that real number corresponds to a real numbered address of the tube. So we've got these infinitesimally thin tubes, and we're transferring fluids based on the relative concentrations over an infinitesimal amount of time. So that's the setup we're dealing with. The last question is, what exactly do we mean by transferring chemicals? And that's the topic of the next video, because that's a little different direction from this basic setup.